All right, welcome back to another lesson in AP Calculus. Today we're going to talk about L'Hopital's rule. So this is a really helpful theorem for evaluating difficult limits. As it turns out, we've spent a lot of time studying how to solve limits algebraically at the beginning of this course, but not all limits can be solved algebraically. For some of those that we can't solve, we can apply L'Hopital's rule. And then there's even more advanced ways to solve limits and things like that. I find L'Hopital's rule fascinating because it shows how derivatives and limits really are connected. We know that a derivative is actually a limit, and we use these derivative rules that we have derived from our limit definition. Now we're going to be able to go back and show how, now that we have those rules, it can help us find some other limits. So we're going to start with a brief review of algebraic techniques. So for each limit, I want us to demonstrate that the limit, as it is written, results in an indeterminate form. Then we'll use algebraic techniques just like we've already done before. So a little bit of review here, but it's important. All right. So first of all, let's confirm that at this moment right now, direct substitution results in what we call an indeterminate form. If I plug in -1 for x, I get -1 squared is 1 times 2 is 2, 2 minus 2 is 0, and -1 plus 1 is 0. So this is an indeterminate form. Keep in mind, we're not saying divide by a true 0. This 0 here, since we're trying to value a limit, is actually a value approaching 0. So a value approaching 0 divided by another value approaching 0, we don't know what that is. So because it's indeterminate, we will use algebraic techniques here to see if we can't evaluate this. I'm going to factor out a 2. And then that becomes, if I factor out a 2, note that that's 2 times x squared minus 1. So that's x minus 1, x plus 1, the difference of 2 squares. I can then reduce those, and I can try again, this time using direct substitution, and I get 2 times -1 minus 1, which is 2 times the -2, so -4. So that's the value of that limit. All right, let's do another one. What about the limit as x approaches infinity? Let's plug in directly infinity. Now, infinity, of course, is not a number, but we're talking about a number approaching infinity, so we just usually write it like that. So a number approaching infinity squared is infinity, times 3 would be infinity. Now, minusing 1 from infinity, that a number approaching infinity minus 1 is still a number approaching infinity. And this is a number approaching infinity squared times 2 plus 1, that's another number approaching infinity. So we don't know what this is. A number approaching infinity divided by another number approaching infinity, we don't know what that is. That's an indeterminate form. So let's do some algebraic techniques. Now, when you're dealing with the limit as x approaches infinity, we're actually doing something kind of weird. We factor out the largest power instead of the smallest common power. And the reason why we do that, 1 divided by x squared, because 1 over x squared, or x to the -2. The reason why we do that is because we're using the property that a number approaching any infinity to a negative power is going to 0. So again, I'll factor out x squared on the bottom. That's the biggest exponent on x. And then I get plus 1 times x to the -2. Those reduce. And we know when we direct substitute that a number going to infinity to a negative power means 1 over infinity squared. 1 divided by a number going to infinity is a number going to 0. So that's just automatically going to 0. So this becomes 3 over 2. And you might remember your rules from algebra class that when they have a rational function like this, that if the degree of the numerator and the denominator are the same, that we have a horizontal asymptote right there at the ratio of the leading coefficients. And a horizontal asymptote is simply a value, a y value that we approach as x goes to either positive or negative infinity. All right, let's take a look at the next one. Looking at the limit as x approaches 7. Again, we want to demonstrate that as it's written, this is indeterminate. So that becomes the square root of 9 minus 3 over the square root of 0. Square root of 9 is 3. 3 minus 3 is 0. And 0 over 0 is... Oh, I'm sorry. There's no square root on the bottom. It doesn't change anything, but I don't know why I added one. There we go. So 0 over 0, that's an indeterminate form. But we can multiply the top and bottom by the conjugate. Plus 3. We get the square root of x plus 2 plus 3 on top and bottom. So x plus 2 times square root of x plus 2 is just x plus 2. The square roots will cancel out. And then this becomes 3 times the square root of x plus 2 minus 3 times the square root of x plus 2. That's going to cancel out. So we just have then a minus 9 over. And the secret here is not to try and expand that. Because if you do, it doesn't help you. We're hoping to cancel out that x minus 7 factor. And if you expand it, then you got to refactor, and it's not easy. All right, it does reduce. So now I can plug in the 7. And I get 1 over the square root of 9 is 3, and 3 plus 3 is 6. So 1/6 is that limit. All right, so let's talk a little about indeterminate forms. Now, this is not something for you to memorize. It's something for you to recognize. And these should be logical to you. You should look at these indeterminate forms, and it should make sense that they're indeterminate. So a number going to 0 divided by another number going to 0 is indeterminate. We don't know what that could be. It could be that those two numbers are going to 0 at the same rate and that they actually reduce out or something like that. We don't know. It's indeterminate. Well, what about a number going to 0 times a number going to infinity? Well, that, again, could be anything. It could be 0 if the number going to 0 is going to 0 really quickly. It could be a number going to infinity if instead one number is going to 0 slowly, the other number is going to infinity quickly, and so then the infinity wins out. Infinity divided by infinity, we talked about that. An infinite number minus another infinite number, again, it depends which one's bigger. You know, if the number going, you know, if this infinity is going to, you know, it doesn't make sense to say a bigger infinity, I know, but this is going to infinity faster than that one, then we're going to have a negative answer. Vice versa if the other were true. And here's something that I don't think we've seen too much of. 0 to a 0 power. Well, we know that, you know, anything to the 0 power is 1, but, you know, but this is a little different situation. Remember, this is a number going to 0 to the power of a number going to 0. And that really is indeterminate. We don't know exactly what that is. Likewise, a number going to 1 to the power of infinity. You know, 1 to any power is simply 1. But if the number's not exactly 1, you know, and the power is going to infinity, if this was slightly bigger than 1, you know, maybe this is going to an infinity. Maybe it's going to like 3. We don't know. It could be anything. And then, you know, here's kind of the reverse of that a number going to infinity to a power going to 0. So these are kind of new for us, but I hope they make sense. Just keep in mind that not everything that has an infinity in it is indeterminate. Notice that we don't have an infinity plus an infinity. We don't have an infinity times infinity because those are not indeterminate. A number going to infinity plus a number going to infinity is going to infinity even faster. So not everything is indeterminate. It should make sense, though. And then I just have a quick note here to remind you that, don't, 0 to 0 power, you type that in a calculator, it might say indeterminate, or it might say, it would probably say like 1. Just keep in mind that, that's not exactly what's happening here. If this was a true 0 here, then yes, any number to the 0 power is 1. But because these are numbers approaching it, we have a little different situation. So some limits in determinate form cannot be evaluated algebraically. We talked about it a little while ago. In the case of 0 over 0 or infinity over infinity, we can, I said we must, but we really can use L'Hopital's rule, or we can try it. Again, L'Hopital's is not going to work for everything, but it'll work for a lot of things. So in this case, and in this case, so that takes care of 2 out of the 6. What is that? 7 different cases. So yeah, it doesn't seem like a lot, but as long as we can get it in that form, we can use L'Hopital. So we'll see how that kind of works out. All right, so I want to talk a little bit about, the formal theorem here. So what is L'Hopital's rule? L'Hopital's rule says that if f and g are differentiable on an open interval containing c, again, except possibly at c, there's that except part, then if the limit as x approaches c of f of x is 0, and the limit as x approaches g of x is 0, or the limit of f of x and g of x is positive or negative infinity, then if the limit exists, then the limit of the original limit is equal to the limit of their derivatives. So if you get this 0 over 0 or infinity over infinity, you can take the derivative of the top and the derivative of the bottom. Now, we're not using like quotient or anything. It's just derivative of the top, derivative of the bottom, and try again. All right? The important consideration is that L'Hopital's can only be used when direct substitution into the original limit has the indeterminate form of 0 over 0 or infinity over infinity. And, you have to demonstrate this fact. I haven't seen in the grading on the AP exam where they care about you establishing an open interval of differentiability, but they care about that fact. You must establish that is true, okay? So the proof for L'Hopital's in general is a little beyond the scope of this class, but the proof for the special case there's several different cases we have to consider, but the proof for one of these special cases is actually quite approachable. So I do want to go ahead and give that a try. Anytime the proof is approachable, I think it helps you to understand it. So let's just take a look at that case. What about the case of the 0 over 0, and we'll say that g prime of c does not equal 0. That just takes care of us not having to worry about the divide by 0 case and things like that. So let's start. What we're trying to show this relationship here, okay? That's the goal that we're working towards. So let's start with the left-hand side. We're going to start with the fact that we're asked what the limit as x approaches a value c of f of x over g of x, okay? Okay, so if that's true, then let's take a look at this. I'm getting pins going, all right. We can say f of x minus f of c over g of x minus g of c. I should be able to say that. Why can I say that? Well, that's because we're assuming, remember, right? We're starting with the special case that f of c is 0 and g of c is 0. So this is an important realization here, that if you try and apply L'Hopital's when the original derivative, you plug in the original derivative, you get like 3 over 5, and you apply L'Hopital's, you are not going to get 3 over 5. You see, L'Hopital's does not work when you try and use it when you shouldn't. It will give you a wrong answer, because this statement here, this step in the proof doesn't apply. But because f of c and g of c were 0, then subtracting 0 from f of x doesn't change anything. So very important consideration there. All right, and then we'll take the limit as x approaches c of, and we'll simply divide here by x minus c. Okay. Okay. So now what does that say? Well, I can split this limit up and I can apply that to there and that to there. Remember, we can split limits up over division. And this top part here, what is that? That is the alternative definition of the derivative of f at c. So that is f prime of c over g prime of c. So what we're saying here is that this limit is equal to that, provided that that exists. So we'll have to see what happens when that doesn't. So, but that's a special case there, and that's the idea of how it works, that relationship between the two. All right, let's get right to applying it. Okay, so let's evaluate. I'm going to plug in 0. What I'm going to do is show that e to the 3 times 0 minus 1. E to the 0 is 1, and 1 minus 1 is 0. And then, of course, if I plug in 0 for x, I get 0. So, because the limit as x approaches 0 of e to the 3x minus 1 equals 0. And the limit, let's go back and let me show what we're saying here. Remember, we have to establish this fact here, okay? We have to take the limit of the top and the bottom. So the limit as x approaches 0 of x is equal to 0, then by L'Hopital's rule, or L'Hopital's, is that how you spell L'Hopital's? I thought it wasn't. Yeah, I got it. That's not right. Let me fix that. L'Hopital's. I got an I and a T displaced. You know, I dotted my T and crossed my I. That's not good. All right, so by L'Hopital's. By the way, just while I'm on this spelling issue, ironically enough, the spelling of L'Hopital's rule is quite a matter of contention. You might see it spelled Le Hospitals. It's still with a S. It's still the same pronunciation. It's just a difference between transliterating French and all that stuff to English. So just don't worry about it. But it's L'Hopital's rule. All right, so by L'Hopital's, we know that this limit here of e to the 3x minus 1 over x must be equal to the limit as x approaches 0 of, we take the derivative of the top, which is e to the u times u prime, and the derivative of 1 is 0, and the derivative of x is just equal to 1. So we now plug in 0, and e to the 0 is 0. Sorry, e to the 0 is 1, times 3 is 3. And so 3 over 1 is 3. And so that's kind of how it works. The key thing to say when using this, if it's a multiple choice question, then you don't have to worry about justification. But on a free response, which is where these have typically lied, make sure you cite the theorem. Make sure you establish that the numerator's limit goes to 0 or infinity and the denominator goes, which is good because it'll keep you from using it at the wrong time anyway. So not a lot of writing to justify it, but a little bit. All right, let's try this one. Okay, if I were to plug in negative infinity here, negative infinity squared is just infinity. E to the negative infinity becomes e to the positive infinity, which is also infinity. So let's establish the conditions for L'Hopital's that the limit as x approaches some value of the numerator is infinity. And the limit as x approaches some value of the denominator is also infinity. So by L'Hopital's, or just something you can just say L'Hop, we can say that this limit here is equal to this limit here. And that becomes 2x over e to the negative x is e to the negative x. I'm getting that thing again where it's not picking up the pencil here. E to the negative x times a negative 1. All right, now let's try that. So I plug in infinity, I get infinity over a negative infinity. Well, that still didn't work, but let's try L'Hopital's again. So the limit as x approaches negative infinity of 2 times a negative infinity, oops, I don't want to plug it in, I just want to say it this time, is equal to negative infinity. And the limit as x approaches negative infinity of negative e to the negative x is also negative infinity. So again, by L'Hopital's, I know that the limit as x approaches negative infinity of 2x over negative e to the negative x must actually be the same, if it exists, as the limit as x approaches negative infinity of the derivative of the top is 2, and the derivative of the bottom, e to the negative, derivative e to the negative x is e to the negative x times negative 1, so the negative will cancel out. So when I plug in now, I get 2 over infinity. 2 divided by a number going to infinity is in fact 0. So this limit here must be 0, but we had to apply L'Hopital's twice. Let's go back and look at it and see, if this was a multiple choice question, would you go through all this work? Well, I would argue you don't have to. If you remember the fact that exponentials are much faster than polynomials. You've probably heard the expression growing exponentially. That means really fast. They don't say growing polynomially. Polynomial time increase is not nearly as fast. So while in the original problem, we plugged in negative infinity. Both the numerator and the denominator were going to infinity, but the rate at which the denominator is going to infinity is many, many orders faster than the numerator. So you're really dividing a small number by a much, much, much bigger number, and that difference is getting greater over time. So it would definitely go to 0. But we've been kind of taking that for granted. Now we can show it's true with L'Hopital's. Okay, let's try the next one. Okay, if we plug in 0 for x, we get cosine of 0 is 1. 1 minus 1 is 0 over 0 squared. This is really similar to something we've seen before. We have seen that the limit of 1 minus cosine x over x is 0. We saw that as one of our formulas that we memorized. But this is not exactly the same thing because it's over x squared. And in fact, it ends up having a big impact. So let's take a look. To apply L'Hopital's, I need to establish that I have an indeterminate form of either infinity on top and infinity on bottom, or 0 on top, 0 on bottom. Well, we agree that that's 0. And the limit on the bottom, the limit as x approaches 0 of x squared, just by direct substitution, is also 0. So by L'Hopital's, we know that this limit must be equal to, remember, very important to show this step, the derivative of cosine is negative sine. The derivative of 1 will just go away. And then the derivative of x squared is 2x. So if I plug in 0 now, unfortunately, again, the same issue. So I'll try it again, though, just kind of whittling away here. The limit as x approaches 0 of negative sine of x is 0. And the limit as x approaches 0 of 2x is also 0. So again, by L'Hopital's, a second time, L'Hopital's rule, we can say that this limit as x approaches 0 of negative cosine of x over 2. Now, if I plug in now, the cosine of 0 is 1, so this just equals a negative 1 over 2. Quite an interesting, surprising result limit, I think, that if you cosine of x minus 1, if this was over just a single x, you get 0, but because it's over x squared, you get negative a half, which I think is kind of weird. All right, so I have some practice problems to do, but there's a mistake on this first one right here. So if you have the notes handout, maybe I fixed it by now, but at this moment, this should actually be a minus, okay? Otherwise, you would not apply L'Hopital's rule, which probably wouldn't be a bad example to check. All right, so do those 4 problems, and then we will go over it. All right, let's take a look at the limit of the numerator. X squared plus 4x minus 21. It's 9 plus 12 is 21 minus 21 is 0. So that limit is going to 0. The limit as x approaches 3 of x minus 3 is definitely also going to 0. So by L'Hopital's, we know that this limit is equal to 2x plus 4 over x minus, the derivative of x minus 3 is actually just 1, not x. So I can plug in directly, and I get 6 plus 4 is 10. Which is what you would get if you did this algebraically, because you would factors as x minus 3, x plus 7. The x minus 3's cancel. So it works the same. All right, let's try the next one. The limit as x approaches pi over 4 of the cosine of 2 times pi over 4, cosine of 2x, well, that becomes the cosine of 2 times pi over 4, which is the cosine of pi over 2, which is 0. And the limit as x approaches pi over 4 of 2 pi minus 8x. Well, 8 divided by 4 is 2, so that's 2 pi minus 2 pi. That's also 0. So we can then apply L'Hopital's rule. Simply take the derivative of the numerator, which is a negative sine 2x, times the chain rule would be a 2. So we put a 2 there. And the denominator just becomes a negative 8. So now when I plug in pi over 4, I end up with negative 2 times the sine of pi over 2. The sine of pi over 2 is 1. So this is a negative 2 over a negative 8, which is a 1/4, which is what that limit is equal to. I'm not sure of how you would do that algebraically. So I think, maybe with this double angle formula, maybe you could get it. But I think this is one where you really would need to have L'Hopital's to do it. Same with this letter C, definitely here. Let's take the limit of the numerator. Limit as x approaches 0 of the sine of x. Sine of 0 is 0. The limit as x approaches 0 of e to the x minus 1. E to the 0 is 1. 1 minus 1 is also 0. So clearly the numerator and the denominator are both going to 0. We can apply L'Hopital's. So I can say that, if it exists, this limit would be equal to the limit of the derivative of the top is cosine. And the derivative of the bottom, well, that's just simply e to the x. Well, the cosine of 0 is 1, and e to the 0 is 1. That makes that limit 1. All right, let's try this one here. The limit as x goes to infinity of e to the negative 3x. Well, e to the negative infinity is 0. Any e to any negative to a negative power means 1 over e to the infinity, and 1 over infinity is 0. And the limit as x approaches infinity of 1 minus 2 to the 1 over x. What does that equal? Well, 1 over infinity, this number is going to 0, right? So this is 2 to the 0 power. Anything to the 0 power is 1. This is going to 1 minus 1 is 0 as well. Kind of an unusual one, right? But we can apply L'Hopital's here. So by L'Hopital's, we can say that this limit It must, if it exists, must equal to this. The derivative of the top is going to be a negative 3e to the negative 3x. Now the derivative of the bottom, 1 will go away to be 0. And we've got 2 to the 1 over x. So we're going to need to use our chain rule and our rules about derivatives of exponentials. So let's remind ourselves what the derivative of 2 to the u is. Well, it's 2 to the u times the natural log of u times u prime. So this becomes negative 2 to the 1 over x times the natural log of 2 times u prime. And 1 over x, the derivative of 1 over x would be a negative 1 over x squared, because that's x to the negative 1, so it becomes negative 1x to the negative 2. Okay, so we can try direct substituting infinity here. What you'll get is that the limit of the numerator is definitely 0, and the limit of the denominator, while not being necessarily completely obvious, is also going to be 0. So it allows us to apply L'Hopital's again. But I'm actually going to do something kind of unusual. I'm going to, first thing I'm going to do is, 2 negatives make plus a positive, right? I'm going to realize that this expression here, 1 over x squared, is actually x to the negative 2. And if that's the case, then I can move it from the denominator to the numerator. Like that, and it becomes a positive x squared. Now, plugging in infinity here, I no longer get a 0 on the bottom. I get the natural log of 2. And on top, I actually get an indeterminate form. So it seems like I've messed it up. But if I can actually evaluate this limit here, I might be able to get a better answer. So this limit here, e to the negative 3x times x squared, this is going to 0 while this is going to infinity. But which one's going there faster? Well, it turns out that this is going to 0 much faster than this. And we could easily show that by redoing this as a separate limit like that. And what I would do is I would say that this is x squared, negative 3x squared over e to the positive 3x. Then, using L'Hopital's a couple of times, we're going to end up with a negative 6 over something like 9e to the 3x after we do it a couple of times, and you can clearly see that this is going to 0 because that e to the 3x never goes away. So for all that reasoning, I think it's fair to say that the numerator is going to 0 and the denominator is not. So this is equal to 0 over the natural log of 2, which is 0. So that's a tough one, but it brings up a nice little discussion about making things indeterminate. So sometimes we must use algebra to get the required indeterminate forms. And I want to show you how to do that. So let's take a look at this one. I've confronted with this limit, and I'm going to try and plug in. So I get e to the negative infinity times the square root of infinity. Well, that's e to the negative infinity. We know that that is going to 0. And the square root of a number going to infinity is still infinity. So this is indeterminate, right? A number going to 0 times a number going to infinity. But it's not the proper indeterminate form. Remember, we have to have 0 over 0 or infinity over infinity plus or minus. But we can easily rewrite this to the square root of x over e to the x, like so. Now, when I evaluate this limit, I get the limit. When I evaluate the numerator and the denominator of the square root of x, well, that's infinity. And the limit as x goes to infinity of e to the x, that's also infinity. So I have infinity over infinity. That's an indeterminate form. So by L'Hopital's, I can evaluate this derivative here to get the same answer. And that ends up being 1/2 x to the negative 1/2 over e to the x. With some simplification, we end up with 1 over 2x to the 1/2 e to the x. Plugging in infinity gives me infinity times 2 times infinity times infinity, so that is 1 over infinity. That is 0. All right, let's take a look at another example. All right, the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. So we could try plugging in immediately. The limit as x approaches 1 from the right, 1 minus 1 divided by the natural log of 1 is 0. So that's 1 over 0. 1 over a number going to 0. So that's infinity, right? And then this here is, let's see, 1 over x minus 1. You could use the graph to help you, that's what it looks like. But as we approach 1 from the right, we're going to positive infinity. So this is infinity minus infinity, which is 0. If you're not sure about this, plug in numbers just slightly bigger than 1, like 1.01. This will become a really small positive number. 1 divided by an infinitely small number is an infinity. Because it's positive, it is positive infinity. So there we go. We have a positive infinity minus infinity. That is indeterminate, but not one of our best forms. So let's try and do a little bit of algebra. Still getting that thing here. So I'm just going to get a common denominator here. I'll make this 1 times x minus 1 over the natural log of x times x minus 1. And then I have minus 1 times the natural log of x over the natural log of x times x minus 1. So then I have the limit as x approaches 1 from the right of x minus 1 minus the natural log of x over the natural log of x times x minus 1. And I seem to have kind of given myself very little space to work, so I'm going to move that over there and create some more space. All right, so let's take the limit now of the numerator. The limit as x approaches 1 from the right would be 1 minus 1 is 0, and the natural log of 1 is 0. So that's 0 minus 0. That's 1 minus 1 is 0 minus 0 is 0. So the numerator's limit is 0. What about the denominators? Well, let's see here. We got natural log of x times x minus 1. Well, the natural log of 1 is 0, and 0 times 0 is 0. So by L'Hopital's, we should be able to do something about this. So I need to take the derivative of the top, which becomes 1 minus, and the derivative of the natural log of x is 1 over x. And the derivative of the bottom is going to require a product rule. So I got to have to do the derivative of the first, 1 over x, times x minus 1, plus the natural log of x, and the derivative of x minus 1 is 1. All right, so what do we end up getting here? Well, we're going to still end up with some indeterminate forms, but let's do some simplifying. I'm going to multiply the top and bottom by x, and I get the limit as x approaches 1 from the right of x minus 1 over x minus 1 plus x times the natural log of x. Okay, well, we're sneaking up on this slowly but surely because I can now do L'Hopital's again. The limit as x approaches 1 from the right of x minus 1 is definitely 0. The limit as x approaches 1 of x minus 1 plus x natural log of x is 1 minus 1 is 0, plus 1 times 0 is 0. So I can use L'Hopital's again, and let me just kind of get rid of that for a second. So by L'Hopital's a second time, I am going to get that this limit is equal to the limit as x approaches 1 from the right. The derivative of the top this time is just a 1, thank goodness. And on the bottom, I got 1 minus 0 plus, again, we're going to use product rule for x times the natural log of x. So the derivative of x is 1, and then times the natural log of x, plus x times 1 over x. And that simplifies down to just a 1. So this is the limit as x approaches 1 from the right of 1 over 1 plus the natural log of x plus 1. So that ends up giving me 1 over 1 plus 0 plus 1 is 2, or 1/2. So we had to use L'Hopital's twice. We had to use some algebra to do that. Pretty exciting stuff. All right, let me try one more here. I got one more problem for us. This one's a tough one, and you don't see this one. I haven't seen this one come up on the AP calculus test. Maybe I saw it once, but this one's pretty tough. But I do see this in a lot of college calculus curriculums. So this is obviously something really important at the next level. It's important for going on in math. So it's good that we talk about it and practice it. So we have a situation here where we, if you plug in infinity, you'll get 1 plus 2 over infinity is 0. So we would end up getting a number going to 1 to a number going to infinity. And this is that indeterminate rule that you're probably not too sure of, right? This one's kind of new for us. So, but that is indeed indeterminate, but it's not of the value that we like. And the problem is this x is an exponent, and we know that logarithms are so useful for that. So what I'm going to do is I'm going to say that the value y, whatever this limit is, if it's a real number, I can assign it y, okay? And what I'm going to do is I'm going to take the natural log of both sides. So I'll say the natural log of y is equal to the natural log of this limit, because I can do that. Okay, so how does that help me? Well, using some log properties here, and that the property that, using some limit properties and some log properties, I can say that we have a limit of a composite function. So I can take the limit of the inside, and then I can use my logarithm property, and I'm going to bring this x down in front. So let's rewrite this as the limit as x approaches infinity of the natural log of 1 plus 2 over x to the x. So just using a little bit of limit properties there that will allow me to use my log property. So I can now say, well, that x can come down because of the properties of logarithms. All right, well, this is beginning to look a little bit more like something we can evaluate. If I plug in infinity here, I get infinity times the natural log of 1, which is 0. So you get a number going to infinity times 0 that's still indeterminate. But let's go ahead and rewrite that as the natural log of 1 plus 2 over x to the negative 1 power. I can move this down, making it 1 over x down here. Okay? Still got that natural log of y hanging out. Now I can see that the limit as x goes to infinity of the natural log of 1 plus 2 over x, well, that is equal to 0. And the limit as x goes to infinity of 1 over x is also 0. So by L'Hopital's, This limit here is the same, if it exists, of this limit. So the derivative of the top, remember, it's u prime over u. So u prime is going to be somewhat nasty, negative 2 over x squared. That's the derivative of the top. And that's the derivative of the inside, the u prime, over u, 1 plus 2 over x. All over the derivative of the bottom is going to be a negative 1 over x squared. But we can make this a lot better really quickly. Okay, I've got this stacked fraction here, and I'm going to multiply the top and bottom of the stacked fraction by x squared. X squared over 1, if that helps you see how that works out. So the natural log of y is equal to the limit as x approaches infinity of negative 2 on top over 1 plus 2 over x over, well, just a negative 1, which we can reduce even more to just positive 2 over 1 plus 2 over x. Now if I plug in infinity, I get 2 over 1, which is 2. So we know that the natural log of y is equal to 2. Well, what was y? Remember back at the beginning of this question, y was what the answer to our limit is, right? Well, so I know that the natural log of that answer is 2. So just doing a little bit of algebra here, I can see that y is equal to e to the second power, which should make sense because this is a definition of e to the second power. E to the n. E to the n is equal to the limit as x goes to infinity of 1 plus n over x to the x. Or as it's probably better written, actually, e to the x is equal to the limit as n goes to infinity of 1 plus x over n to the n. So that is that's one of our definitions of e. So that's the definition of e to the x. Pretty cool, right? Okay, that's it for this lesson. Take care.